Hi, my name is Tim Clegg. I'm a Senior Principal Solution Architect at Oracle. I focus on the enablement of ARM and multi-architectural application development and other OCI developer tools and services. I enjoy doing cloud, networking, security development, automation, orchestration, and communications. I'm a CISSP and I enjoy programming as well as designing and documenting architectural cloud patterns that address relevant business needs. Thanks for joining. Hi, thanks for joining this session. This is going to be tips and tricks for developing multi-architectural software. Today, we're going to be covering quite a few different topics. I will just warn you in advance. This is a pretty deep subject, so we're not going to be able to cover every detail exhaustively for sure, but we'll be able to give you a good solid understanding as you go to embrace multi-architectural application development in Oracle Cloud Infrastructure, or OCI. Today, we're going to be talking about the basics of multi-architectural application development. If you've been developing in x86, 64 architectures and now looking to adopt ARM 64 into your development practice and your environment, this can be really helpful, just covering some of the basic nomenclature, terminology, and things to be aware of. Likewise, we're going to talk about sizing, some different things to keep in mind. And then we'll talk also about container considerations when you're doing multi-architectural applications. And then finally, we'll talk about application binaries and what that might look like for some different languages and just in general in a multi-architectural world. So without further ado, let's jump into it, talking about the basics. First off, some acronyms. It's going to be important. The IT industry, we love acronyms, right? There are two mainstream processor architectures, both of which are offered in Oracle Cloud Infrastructure. One of those is ARM, and that's what we're really talking about today is ARM development. The OS naming, the operating systems typically refer to this as AArch64. Sometimes you'll see it referred to as just ARM as well. Now in the container industry or the container world, this is oftentimes called ARM64. Likewise, when we look at AMD or Intel or x86 64, that's literally what it's called, x86 64, also known as just shortened as x86. Now, when it comes to the container world, typically this is called AMD 64. So just be aware as you start looking into these different tools and services and packaging up containers and the like and building binaries and working with different application binaries and different operating systems, just be aware of some of these different terms. Be important to know about. Now, a platform, this is, if you've not worked with these or heard of these before, it's good to know about just because it's a common format for conveying both the architecture, the operating system, and sometimes optionally a variant if we have that with the processor. So now the exact format, the way it's formatted, varies between tools and ecosystems. So we like to confuse things a little bit. Here are a couple of examples. For the container industry or the container world, when we start talking about Linux ARM64-V8, it's because it's talking about the operating system hyphen the architecture hyphen the variant. Now, again, when we start getting into other ecosystems, such as I'll pick on CrossTool NG, which is a great solution here for cross-compilation of C applications, they'll use architecture hyphen the variant hyphen the operating system. So you'll notice some examples here would be AArch64 -OL86 -Linux -GNU. So we start looking at some of these different differences. Understand, again, the platform in a nutshell is going to be able to convey quickly and concisely the architecture, the operating system, and maybe the variant. Useful to know. Now I want to give you some quick information here about Oracle Cloud Infrastructure because OCI is an industry-leading public and private cloud provider offering different IaaS, infrastructure as a service, software as a service, as well as platform as a service capabilities. We have 39 regions globally, and we have data centers in 21 countries, and 11 of our cloud regions are interconnected with Azure. So if you're looking at a multi-cloud solution or a polyglot cloud architecture, OCI is a really strong platform to be able to interoperate and use. Now, when we start talking about our computing, specifically ARM computing, we have two different flavors or options. OCI A1 compute shapes are powered by Ampere Ultras. And they come in, again, two different flavors. We have bare metal, and then we have virtual machine. You can see some of the differences here. At the end of the day, scalability is incredible with these platforms. And when we look at the cost, the performance, price to performance ratio, when we look at 1 penny per OCPU hour list price, it's incredibly cost effective, not to mention very performant. So again, bare metal as well as virtual machine, scaling anywhere from 1 OCPU all the way up to 160. So a lot of different use cases and options there available for your use. Now, the nice thing about OCI A1 is we get predictable performance. We can scale with ease, lots of different cores and scalability there. The scalability when we're talking about ARM is typically, oftentimes, linear. And so that's a really strong benefit as well for certain use cases and types of jobs. Performance is super strong, great caching and memory bandwidth. So we start looking at different use cases, things like web and app servers, HPC type of applications, media transcoding, AI, machine learning. Some of these different application use cases are terrific, perform really good on OCI A1. So, of course, not limited to those, lots of others as well. And we start looking at the compute instance shapes. Coming from an Intel or AMD world to an ARM world, let's look at some of the similarities between these. So I'm going to look at what OCI offers. These are just a small sampling, clearly. We have a lot of different compute shapes available. But when we look at, for instance, Intel Xeon Platinum 8358 versus the AMD EPYC 7J13 versus the Ampere Ultra Q8030, you can see here some of the similarities. We all support the same number of VNICs. And you can see, again, the shape name on the left there as well. Maximum network bandwidth is going to be the same. Address size is the same, and Indianness is the same. They're all little Indian platforms, 64-bit architectures. Now we start looking at some of the differences. To be expected, we see some with the clock speed, for instance. The number of OCPUs, remember we talked about the denseness and concentration of the number of processing cores. A1 just is incredible. And same thing when we start seeing the number of vCPUs, there's some differences here. We'll notice that multi-threading is not supported on the A1 shapes, which is why the number of vCPUs is lower versus the AMD or the Intel offering. Now, from a memory footprint perspective, very solid, and the number of cores per CPU really tightly aggregated there. So again, some things to be aware of. Clearly, there are lots of others, but this is a quick high-level overview in terms of some of those things just off the get-go to be aware of. Now let's talk about sizing. When we start talking about sizing, remember A1 is not a multi-threaded architecture or platform. So therefore, when we look at the number of OCPUs that we might need or want for an A1 compute shape, that would be the same. Largely, we'll typically start testing by getting the exact number of x86 threads that we're using. Notice how he didn't say the number of cores, but rather threads. This is because depending on your application stack in an x86 world, the number of OCPUs might be different. For instance, if we have a parallelized multi-threading application, we would take the number of cores, and assuming all of the threads are being used, we would double the number of x86 cores to give us an approximate number of A1 OCPUs to begin testing with. So it's, again, assuming 2 threads per core in an x86 world gives us double the number of OCPUs. Now, when we start getting into situations where we have single-threaded applications, we'd start testing by doing a 1-to-1 ratio. Number of x86 cores would be the same number as the A1 OCPUs. So that 1-to-1 ratio, it's not going to be perfect. You're going to have to test, right? And same with a 2-to-1 ratio. It's not going to be perfect, but it gives you a good starting point and a good reference point when you're testing and developing applications. Again, this is for both multi-threaded applications as well as single-threaded. It's going to vary depending on your application and environment. Now, an example here. So we have a multi-threaded application. This is running on a VM standard 3 flex shape. So this is an x86 64 architecture. We have 16 cores allocated to this multi-threaded application, which yields approximately 32 vCPUs. So for testing purposes and begin trying things out, I would start with 32 OCPUs on an VM standard A1 flex shape. AArch64, the ARM. So again, double because it's a multi-threaded application. Looking at another example, which is single-threaded, this situation we have an application that's running on a VM standard E4 flex shape. That's again an x86 64 platform architecture, and it only has 4 cores allocated to it. start testing around 4 OCPUs on an A1 shape. That would render a good starting point, reference point for that particular application. Now we start talking about memory. Memory's memory largely. Not always, but by and large, a 1-to-1 ratio. Whatever you're using on an x86 shape, you could probably go ahead and start and begin testing with that same amount on an A1 shape. Now, from a networking performance perspective, know that each physical host, if you remember back when we were looking at our similarities, you remember that each host has 2 50 gigabit network connections. And so those connections are shared amongst all of the different cores. Now, because we have a denser concentration of cores on an A1 shape versus what we might have with an E4 or an X9, it means that there's potential risk for increased oversubscription on the ARM shape. So I don't want to scare you. This certainly is not meant to scare you by any means. It's simply something to be aware of. As you start to consume different OCI services that are heavy network bandwidth users, things such as OCI block storage or OCI object storage or OCI file system service, these are all services that rely on the underlying network for being able to transport that data to and from that storage service. And of course, developing your own applications or services, if you have services that are very bandwidth intensive, you'd want to be able to take that in mind as well. What that means, again, netting it out, is that because we have a higher number of OCPUs, looking at the bare metal shapes here, for instance, you can see, for the Intel, we have 128 OCPUs, the AMD would have 64, and then on the A1, we would have 160. All of that means is that if we extrapolate that out, and it's not always going to be this way, but I'm kind of simplifying things out, trying to show this principle, that if you just simply divide 100 gigabits divided by the number of OCPUs, break that down, you get a bandwidth per OCPU, and you can see that the A1 is less than 1, meaning you can get in situations where it is oversubscribed. There's more request for bandwidth than we have bandwidth available. So just keep that in mind. It's not the only platform. As you can see, the Intel can result in that as well. You just want to be aware of it and just factor it into your sizing and testing as you develop your application or environment. Now let's talk about containers. Shifting gears a little bit here. When we start talking about containers in a multi-architectural world, what we typically will have is a single container for a single platform. So for instance, if we're developing for both AMD 64 and ARM 64, we'll have 2 container images. Now, we don't want to have to reference each of those container images individually. For instance, in the example here, you'll see we have Hello World Linux AMD 64 v100, and then we have Hello World Linux ARM 64 v100. I don't want to have to reference that in my Kubernetes deployments or other references individually and have to keep track of different container names for different platforms. So therefore, what we do is we tie those together in what we call a manifest. That manifest provides an alias or a friendly name. You can think of it, a link or what have you. It contains an index matching the different container names that we've added to it with their platform specifics. So in other words, the architecture information. So that way I can reference that one name, Hello World Linux v100, which is on the screen here. And as a host fires up and goes to pull down that image, it'll say, oh, I'm an AMD 64 architecture. I need this container. And it'll grab the appropriate container out of that manifest. Likewise, if I'm an ARM 64, if I'm an AH64 platform, it'll go ahead and look at that and say, hey, I need the ARM 64 version. And again, just referencing the one name, the manifest name, I'm able to get that multi-architectural behavioral support without having to fire up different or reference different container names for different platforms. So just be aware of that. Now, when we start looking at building these containers, there are different options. We can do it natively. So in other words, fire up an A1 node and build the containers and push them up to the registry on an A1 instance, or we can also emulate. So I could emulate on an AMD or an Intel OCI shape and then push those up to the registry as well. Native is the fastest. It's definitely kind of an ideal situation. If possible, it's probably usually best to go native. An example shape would be, again, that we've been seeing this, and you'll see this recurringly. The VM standard A1 flex shape, for instance, is a VM shape that would be a great candidate for going ahead and doing the native builds. Now, the alternative is emulation again, which is, it's slower. You can definitely use an AMD or an Intel-based shape for doing that, and it is an option. The reason why I mention it is because sometimes you'll run into situations where you may only have one specific architecture, but you need to build for others. That's where emulation can come and play a factor there. Now, there are a couple of different tools for emulating on different architectures. These certainly not exhaustive again, but these are a couple of tools available. QEMU User Static or QUS. Now, be aware, both of these allow us to be able to emulate ARM on x86, so AArch64 on x86-64. However, only one of these allows us to be able to emulate x86-64 on AArch64. So if you need bidirectional emulation, pick the appropriate tool, right? Take a look at it. And of course, other architectures besides AArch64 are supported as well. So take a look at both of those tools and just know that that's another tool that you can put in your tool belt when needed to be able to build multi-architectural containers. Now, popular container and image management tools include like Docker, Podman, Builda. For those who have worked with containers, these are probably going to be some familiar names and tools, certainly not exhaustive. What I want to do though is take a quick look into the process, a quick high-level view in terms of the process with each of these different common tools for building multi-architectural containers. So the first one is when we start looking at Podman, actually. And you can see here with Podman, it allows us to be able to build two images. So we're going to build an ARM64 image and then an AMD64 image. Then we'll build a manifest that will tie those two together. And then we'll upload all three of those to the OCI container registry. So both the ARM64 image, the AMD64 image, and the manifest all get built and then pushed up to the container registry. And you deploy, wash, rinse, repeat, as needed when you're generating those. Now, when we start looking at Builda, we can build two images and a manifest, which is the hard way, right? We can do that. It's the same process as Podman largely, where you have to build each image and then tie them together in a manifest and push all that up. Or there's a nice handy wrapper that Builda provides, which is Builda Build. And you can easily push those different resources, those different artifacts to the OCI container registry and deploy away to your heart's content. Now, Scopio is a great tool that I just want to mention here, just to put in a little blurb for, just because most of the container tools do allow you to inspect, whether we're looking at an image or a manifest. We can oftentimes inspect, which shows kind of a JSON, usually it's a JSON representation of whatever's contained within that container or manifest. And helpful lines would be like looking at the architecture or the some of those different platform specifics. Scopio goes beyond that and allows for not only inspection but also copying, deleting, syncing, all that good stuff. It's kind of a good, really another good tool for your tool belt, when you're working with containers. And so just wanted to call that out and make mention of Scopio just on a side note. Now we start talking about application binaries. Let's dive into that. There are some general principles that we're going to cover. Again, really broad subject, just disclaimer, broad subject. We're not going to be able to touch everything for everyone, not every language, not every use case and the like, but some general high-level principles here. Compiled languages almost always have to be compiled for the specific platform. Now, that kind of goes without saying, but I'm just calling it out just because it is something that you need to remember and include and factor into your multi-architectural practice. Now, each language is different. Some languages support cross-compilation. Some languages you need to emulation is needed or what have you. It is going to be specific and different for both the platform as well as the language. And so just be aware of that. Now, oftentimes it's easy to think runtime languages, things like interpreted languages like Python or Ruby, they can have there's really nothing to worry about or think about here. And oftentimes that's the case, but there are oftentimes issues from libraries or modules or gems that can come into play here, especially when we think about different extensions or libraries, modules, gems, what have you, that are compiled in C, for instance. There can be implications here. And so while your base Python app, for instance, might be okay, you might have wheel dependencies that are not supported. So just keep that in mind, as you're going through that. Just don't assume that because it's a runtime interpreted language that you're in the clear. No, still need to go through your due diligence and testing for sure. Now, when you're starting out, I'd encourage you to identify your goal. What are you trying to do? Are you trying to decrease your memory footprint? Are you trying to yield the fastest build time? Just get it built as quickly as possible? Or are you looking for, you want to minimize the variability between builds? You want to maintain a high level of consistency across your builds. Different techniques are going to require different tools and different approaches to be able to get different end results. And so you need to be aware of that. Just think about that and say, like, what's my end goal here? What are my operating requirements, my business functional requirements that I need to incorporate here or take into account as you're going into that? For instance, testing is always going to be key, right? And I probably shouldn't need to say that, but it is something to think about. When we look at building binaries, we have different techniques. We have native emulation or native compilation, excuse me, which is the best and ideal. So get an A1 instance, get it configured up exactly like what your production or deployment environment is going to be, supported environment, and build away, compile, build it. Emulation is another option as well. It's slower. So it's, something that's available. Cross compilation is another good option, and it's really fast, but you might get some variability, some unexpected variability. Again, any of these can result in variability as well. So again, testing, test. I can't say that enough when you're doing this. Any sort of multi-architectural development, any development in general, you're going to want to really thoroughly test clearly. Now, some examples here of some different things to keep in mind. Page size differences. This affects the padding of a binary. So it can directly impact the size of a binary. So for instance, when we look at the Oracle Linux page size on x86-64, we see that it's 4096, whereas the page size on AArch64 is at 65,536. So you want to look for those differences and keep that in mind as you're looking at the resulting output binaries, right? Because there could be some big differences in the size just simply from page size differences. Build environments is another area where things, even something as mundane as the directory of the source code or where it's being built, can differ and result in changes to the ELF debug headers, for instance. Now, when you're looking at C, don't forget the optimizations. GCC is super awesome. It's really intelligent. Take a look at what optimizations it's using. And don't forget the different CPU flags and features. So those can impact what and how GCC builds and compiles. So make sure you look at proc CPU info, for instance, and in your build environment and desired environment when you're trying to look at why things might be different than you expect. Tool chains differ between different sources. For instance, ARM GNU toolchain might have 11.2. For the GCC version, Oracle Linux 7, 8, 9 are all different versions. These can all behave differently. So you really want to take that into account. glibc versions, everything kind of going with that. The whole tool chain can be vastly different between different versions of operating systems or of tool chain providers. So keep that in mind and factor that into your practice as well, your development and analysis. And if you do cross-compile, I'll throw a blurb out here. CrossTool NG is terrific. We have great support for Oracle Linux with it, and it's a great cross-compilation tool chain that can help you build cross-compilation tool chains, I should say, using and build and manage those. Now, some tools are not AArch64 compatible, such as strace, so keep that in mind. Java is largely portable. However, keep in mind JNI may or may not be. So there's a lot of different variables. We can't go into all the details here, but just recognize that, if you are using JNI, for instance, there could be some increased complexity. With Go does support cross-compilation out of the box. There can be differences between the native compilation and cross-compilation. So keep that in mind. Just know that that's something that can happen. With Python, as I mentioned earlier, wheels can be architecture specific. Not all support ARM64, so watch out and test. Maybe your application Python code is fine, but there's a dependency, a wheel dependency that is not portable, that is not multi-architectural, does not support ARM64. Watch out for it. Test it. Ruby, largely portable. Like I mentioned too, though, certain gems are compiled in C, right? They're built in C and then used in compiled. So that can be problematic. Keep that in mind and factor that in. So in summary, application binaries will be different. You're going to want to build and compile twice, once per architecture. So assuming you're supporting both x86 64 and AArch64, you do it twice. Each language is going to be different, and OSs, operating systems, there are a lot of different variables. Some are easy, some are not. Take a look at it. Spend your time in your due diligence. Remember that container images will be different. You're going to want to build those for each platform, or at least each architecture, and providing binaries for that appropriate architecture clearly in that specific Docker image, or that container image. And then when we look at tuning parameters, don't forget the operating system level aspects or the tool chain differences, the optimizers, all that good stuff. And then from a sizing perspective, memory usage, all that good stuff. Don't forget cores versus threads, multi-threaded, single-threaded, and network bandwidth to take that and keep that in mind. Some different links that you can take a look at and reference later if you'd like to. Here's some different articles as well as reference on some of the different OCI compute shapes. And finally, I'd like to thank you for joining me. Have a great rest of your day. Thank you.